The question that I have is, could you explain the graphical method of solving 2D seepage problems? Here is the graphical method. To illustrate this method, I'm going to consider the seepage tank problem. The first step is to identify the boundaries. So what are the boundaries for this problem? Well, the boundaries define the domain through which the water flow takes place. So in this problem, these are the boundaries: A to B, B to C, C to D, D to E, E to F, F to G, G to H, H to A. It turns out that a given boundary will either be an equipotential line or a seepage line. So let's work on line AB, which is from here to here. So I'm going to take 2 points I and J randomly on that line and calculate the total head at these 2 points. And I'm going to take this as the datum. So with respect to the datum, you can see HI is Z1 plus Y1, HJ is Z1 plus Y1 again, and therefore the heads at these 2 points are equal to each other, and by definition AB is therefore an equipotential line. By the same approach, we can easily show that EF is also an equipotential line. The total head on that line is Z2 plus Y2. What about the rest of the boundary? Well, it turns out all the other boundaries are flow lines. Remember the definition of flow lines, right? The velocity vector of water flow at a given point is tangent to the flow line that passes through that point, right? So let me consider the bottom of the tank HG. Let me take a point K. We know that the tank bottom is impermeable, and therefore if the water is going to flow, it has to flow parallel to the tank bottom, not perpendicular. In other words, this component of the velocity vector has to be equal to 0 at this point. And this is true for any point on that line. And therefore, HG is a flow line because the velocity vector is parallel to that. By the same rationale, you can see all of these are flow lines. I marked all of them in green here. Now we are ready to sketch the flow net, but there are some rules to follow. There are several, but these basic rules would be sufficient for us to deal with this problem right here. Number 1, these lines, equipotential and flow lines, are smooth. Number 2, they intersect at 90 degrees to each other. Number 3, you want to keep the number of flow lines and equipotential lines as few as possible in the beginning. You can come back and make the flow net finer later. Number 4, we want to try to get a square flow net as much as possible, and I'll explain the reason in the next slide. Square means they are curvilinear squares, not squares consisting of straight lines, because these flow lines and equipotential lines are curves, right? So you want to try to get curvilinear squares. Say I want to start a flow line from here. So you start at 90 degrees to this equipotential line, right? And then you go smoothly around the sheet pile wall like that, and also end up at 90 degrees to this equipotential line, this one right there. Let's go ahead and do one more. So I'm going to start from here. So I got 2 flow lines in there, and I'm going to do an equipotential line starting from here. So you start from here, again 90 degrees to this, because this line is a flow line, right? Okay, so every time you intersect one of these, you want to make sure you are intersecting at roughly 90 degrees over here. So all of these should be 90 degrees. So I sketched a few more equipotential lines. This one, this one, this one, this one. I want to keep these roughly curvilinear squares. You don't have to be too nervous about it, and it turns out that even a flow net like this, which is kind of decent but not the best, but even a flow net like this will give you surprisingly accurate estimates for the volume rate of flow and pore water pressure and so on. Let's do some analysis with this flow net. Let me first define what is called a flow channel. A flow channel is the region confined between two adjacent flow lines. Like for example, if I take this flow line and this flow line, this is the region confined between these two flow lines, right? And this region is what is called a flow channel. So in this flow net, I have three of those. Here is one channel, here is one channel, and here is one channel. These flow channels can be compared to pipes because the flow channels are confined between flow lines, and we know the meaning of a flow line, right? Water cannot flow across a flow line, and therefore flow line can be thought of as an impermeable boundary for this region, just like in a pipe. So in this flow net, we have three pipes carrying water from the upstream to downstream side. So if you can figure out the quantity of water that each pipe carries, then I can sum it up in order to find the total quantity of water flow through the soil, right? Let me consider the curvilinear region KLMN and assume that the average distance this way is little a, this way is little b. We know the water is flowing in this direction, right? And I'm going to further assume that this is a perfect rectangle, like a little pipe, right? Say the total head on this equipotential line is HKL, and on this equipotential line is HMN. Then the hydraulic gradient in this region can be, on an average sense, written like this: I equals HKL minus HML MN divided by B. We'll for now call this difference as delta H1, and therefore the hydraulic gradient in that region is delta H1 divided by B. Assuming the soil to be isotropic, then the velocity is given by this equation right here, and then I can now calculate delta Q, which is the rate of seepage through this pipe right here, simply by multiplying the velocity by little a, and therefore it works out to be this right here. If we have a square flow net, then A is roughly equal to B, and therefore delta Q becomes equal to K times delta H1. Now we know that the quantity of water that flows through this region right here must be exactly equal to the quantity of water that flows through this region, right? And by equating these two, we find this very interesting result. That is, the head drop between this line and this line must be exactly equal to the head drop between this line and this line. So we can extend this analysis all the way just to show that the head drop between two adjacent equipotential lines in a square flow net is a constant. We can easily calculate that as shown here. We know the total head on this line, the upstream line, is H1, right? And then we know the total head on this downstream line is H2. So if I subtract one from the other, that is the total drop when we go from the upstream side to the downstream side. And there are 1, 2, 3, 4, 5, 6 equal drops, right? And we'll call that as ends of E. Ends of E is the number of equipotential drops. So all we have to do is to take this difference between the upstream and the downstream side heads and divide that by NE. We get the little delta H, which is the head drop between two adjacent equipotential lines. Now we can evaluate the total head at any of these equipotential lines. So here it is H1, here it is H1 minus delta H, and here it is H1 minus 2 delta H, and here it is H1 minus 3 delta H, and here it is H1 minus 4 delta H, and over here H1 minus 5 delta H, and over here it should be H1 minus 6 delta H, which should be equal to H2. Another important result from this equation. There's nothing in this equation that ties this equation to this particular pipe. In other words, if I repeated this analysis for this pipe, I would have gotten the same result. So what that means is delta Q through pipe 1 equals delta Q through pipe 2 equals delta Q through pipe 3. In other words, each of these pipes carry the same amount of water. So this is another result from the fact that the flow net is a square flow net. So now I can find the total flow through the soil simply by multiplying this delta Q by the number of flow channels that I have here. So, of course, for this specific problem, I have 3 flow channels, but we'll just derive this equation in a more general way. So Q works out to be K multiplied by big delta H multiplied by NF over NE, where NF is the number of flow channels, NE is the number of equipotential drops. So we ended up with a very simple equation for the volume rate of flow through the soil. Also note that big delta H here is geometrically equal to this distance, difference in the elevations of the two water levels. Another common thing we do is to calculate the pore water pressure at a given point in soil. Say we are interested in calculating the pore water pressure at point R. These are the steps for doing that. You go ahead and calculate the total point at point R, and for this flow net, you can see the total head at point R would be the total head on line AB minus roughly about 4.5 times the increment between two adjacent potential lines, right? In other words, HR equals HAB minus 4.5 times little delta H. Then you calculate the pressure head at point R, simply by subtracting the elevation head from the total head, like I have done over here. Once you have the pressure head at that particular point, your pore water pressure at that point is simply the pressure head multiplied by the unit weight of water. That's it. So that's the general procedure that can be applied to any point in the soil where the water flow takes place. The third most common thing we do is to calculate factor of safety against piping failure due to boiling. We have discussed this in some of the previous videos, right? If boiling is going to happen, it's going to happen in this toe region. This is where the water is flowing vertically up. In an approximate sense, you could take this little element right here, the element at the toe region, and consider that as a pipe that is being held vertically up. So what we do is we go ahead and calculate a factor of safety by this equation, where F, the factor of safety, equals I critical divided by I toe. I toe here is the hydraulic gradient in this toe region, which can be approximately calculated using this equation, where I toe equal delta H, which is the head difference between two adjacent equipotential lines, divided by this distance, delta L. I critical is the critical hydraulic gradient. That is the hydraulic gradient at which boiling would take place. And you might recall from the one-dimensional analysis of a vertical tube, we came up with this expression for I critical, right? I critical equals gamma prime divided by gamma sub W. Gamma prime is the buoyant density of the soil. Gamma sub W is the density of water. So if I toe is very small, we have a large factor of safety, but if I toe is large, then we have a very small factor of safety.